Right, so last week we were talking about electron configurations, which was basically a way to show where electrons are within an atom. So for example, if we took um, the element sulfur and we wanted to make the electron or show the electron configuration for sulfur, it would look like this: 1s2, meaning I have two electrons in the 1s orbital, 2s2, two electrons in the 2s orbital, 2p6, 3s2, and 3p4. This would be the electron configuration for sulfur. And remember, what we've got here is we've got the first energy level with its one orbital that it can hold. We've got the second energy level, which can hold two different sublevels, and then we've got the third energy level here. The third energy level can hold three sublevels, but for sulfur it only fills up to the p orbital. So here's our last energy level for sulfur. This is the highest energy level for sulfur, the third energy level. And in that third level, we've got 4, 5, 6 electrons. And those electrons that are in the very last energy level, or in the highest energy level, those are called the valence electrons. So the electrons that are in the very last energy level, the very outer energy level, they're called the valence electrons. And the valence electrons are important in chemistry because the valence electrons are what are responsible for bonding. So whenever we have two elements that are bonded together, they are bonded together because of these outer shell electrons. These inner electrons in here really don't have anything to do with the bonding that's going on between different elements. So we really only care about the outer energy shell electrons, which we call valence electrons. Now, that brings us to electron dot diagrams. Since we're only interested in the outer shell electrons, the very outer electrons, and we don't really care about the electrons that are in towards the middle, we can draw these electron dot diagrams which show how many valence electrons different elements have. So if I wanted to do an electron dot diagram for sulfur, we just got done saying that sulfur has 6 valence electrons. 6 valence electrons. So what I can do for my electron dot diagram is I can take the symbol for sulfur, which is just S, and then what I'm going to do is I'm going to put dots around the outside of the symbol. And I'm going to basically break it up into 4 sides. So I've got the top, the bottom, the left, and the right, in where I can put dots. And I can put 2 dots on either side of the symbol. So I can put 2 dots up here, 2 dots here, 2 dots here, and 2 dots here. For sulfur, we've got 6 valence electrons. So here's how I'm going to do this for sulfur. I'm going to go 1, 2, 3, 4, 5, 6. And this would be the diagram for sulfur, showing that it's got 6 valence electrons to work with on that outer shell. And I could do that for any element. So let's say I wanted to do it for, let's say, fluorine. Fluorine, if I go to the periodic table, we look, it's right here. It has 7 valence electrons. And so for fluorine, if I'm going to do the same thing that I've got here, I'm going to do 1, 2, 3, 4, 5, 6, 7. And there's the electron dot diagram for fluorine with its 7 valence electrons. Another example, hydrogen only has 1 valence electron, so it would just have 1 dot. Carbon would have 4 valence electrons, so 1, 2, 3, 4, like that. Notice when I draw on the dots, it kind of helps to do 1 dot at a time on each side before you start doubling up. especially when we get down here to drawing Lewis structures and things. It helps to just put one dot on each side before you start doubling electrons up on each side. Another example would be like magnesium with 2 valence electrons, so 1, 2, like that. And remember, we've already talked about this before, but the reason I know, just by looking at the periodic table, the reason I know how many valence electrons each has is it depends on where it falls in the periodic table. So again, we've talked about this before, and you should have this on your periodic table if you don't already have it. But remember that all the elements in this column right here, they all have 1 valence electron. These elements here have 2 electrons, 2 valence electrons. If we come over here, these elements have 3 valence electrons, and then we can just continue that pattern. So 4, 5, 6, 7, and these guys have 8 valence electrons. We kind of leave out the transition metals for now because they have a different way of filling up their orbitals. Remember, we found that out with the d orbitals and things like that, so we kind of leave those out of that pattern. But for these guys here, this is the pattern that we follow for how many valence electrons they have. So if I want to draw a dot diagram for anything in this column here, I know that for any of these elements here, like nitrogen, phosphorus, arsenic, these guys are going to have 5 dots around the outside of theirs. All right, so if we come back to this. Now, here's the thing with most elements. They want to gain, or they want to have 8 electrons in their outer shell. Because if they can get 8 electrons in that outer shell, that means that they are very stable. They're very stable. So remember we talked about how this column over here with helium, neon, argon, krypton, all these are called the noble gases. And they call them noble gases because they don't react with anything. And the reason they don't react with anything is because they already have 8 valence electrons in their outer shell, and that makes them stable. So they don't need to bond with anything in order to gain those or to get 8 electrons in their outer shell. However, all of these guys over here, none of these guys have 8 valence electrons. And they're constantly trying to get 8 electrons because if they can get 8 electrons in their outer shell, that means they become stable. And we call that rule, by the way, sliding over here. Make sure you get this down. This is called the octet rule. The octet rule says that atoms tend to gain, lose, or share electrons in order to get 8 electrons in their outer energy shell. We should make a quick note here. Remember that, so hydrogen and helium, for them to get a full energy, a full outer energy shell, they actually only need 2 electrons. They don't need 8, they only need 2. But you can still think about that as for them, that's their octet, is getting 2 electrons based on where they're at with the periodic table here, right? So hydrogen, it has 1 valence electron, but it only has 1 energy level. It only has 1, and that first energy level can only fit 2 electrons anyways, and so hydrogen just needs to get 1 more electron, and if it has 2, full shell. Just like helium here. Helium has 2 electrons in that first shell, and that's the only shell it has, and so it's got a full octet with really only having 2 electrons. So just kind of keep that in mind. So we've got these atoms, and they're all in the hunt for getting 8 electrons in that outer shell. And there's the ways that they can do that, remember, are gaining and losing electrons. So they can like give electrons away or take electrons, which we've already talked about. Earlier in the school year, we talked about that these right here, this is for ionic bonds. And we learned about ionic bonding and how to name ionic bonds and things like that. And then we've got sharing electrons, and this is for covalent bonds. Covalent bonds, which we really didn't talk too much about. And so if we come back over here and we look at these electron dot diagrams, and I've got these elements here, and none of them have 8 electrons. So I've got magnesium with 2. It wants to get 6 more. I've got sulfur with 6 electrons. It wants to get just 2 more, and then it'll be happy. Hydrogen, remember, just wants 1 more electron. It'll be happy. Carbon wants to get 4 more. It'll be stable. And fluorine just needs to get 1 more electron to be happy. And so if one option for magnesium, for example, could be, let's say it, since it can just get rid of these 2, if it could get rid of these 2, that means it would drop down to the next energy level, and it would have a full shell if it could get rid of these. And sulfur wants to just get 2 more, and it'll be full. And so we saw that with ionic bonds, what can happen is that magnesium can give these electrons over to sulfur, and what will happen is, since magnesium loses those 2 electrons, we saw that it would get a positive charge of +2, and then sulfur, since it gains those 2 electrons, we get a charge of -2. And we saw that because they're oppositely charged, we would get magnesium sulfide. They would bond together because they're opposite charges, and that's giving and taking electrons. So that's one way that atoms can get a full octet. They can give away electrons, or they can gain electrons. What we're going to focus on here is not the giving and taking of electrons. We're going to more focus on the sharing of electrons. So if we look, for example, at, we'll take a look at fluorine, and that brings us to Lewis dot structures here. Let's talk about fluorine, or the F2 molecule. So remember we talked about early in the year diatomic molecules. And those were most of those gases that we see on the periodic table, like fluorine or chlorine or bromine, iodine. All of those, we said, when they're in their elemental state, just pure chlorine or pure bromine or pure iodine, that it wouldn't just be single atoms of chlorine. They would actually be 2 atoms of chlorine bonded together, or 2 atoms of bromine, or 2 atoms of iodine bonded together. And those we call diatomic molecules. Now we're going to see why it is that we find those that way. So if we take a look at, for example, fluorine, if I write out the dot diagram for it, it looks like this. It's got 7 electrons around it. It just needs to get 1 more. It just needs 1 more electron right there, and it will be full. Well, what it can do is, if I've got another fluorine atom here with its 7 electrons, what they can do is they can take these 2 electrons here, and they can share them between these 2 atoms. And if they do that, then they both end up with 8 electrons. And so how we would draw that is, we would say we're going to put a line here, and this line is essentially like we took these 2 electrons and we put them together into this right here. This line is signifying a bond of 2 electrons that are being shared between 2 fluorine atoms. The rest of these electrons would just still be there, so we put those on there like so. And so now, if I look, what I'm showing is I've got a bond of 2 electrons, a single bond, 2 electrons, that is holding these 2 atoms together. And if I count up how many electrons each atom has, we'll see that it has 8 electrons, which is what they want. So if I look at this fluorine right here, this bond of 2 electrons, since it's shared, these 2 electrons count towards this fluorine, as well as this fluorine. So if I count up the electrons for this one on the left, I've got 1, 2, 3, 4, 5, 6, and then 7, 8. So 8 electrons for fluorine, which is what it wanted, so it's happy, it's stable. And then if I look at this fluorine, it also has 1, 2, 3, 4, 5, 6, 7, 8. Notice those two electrons, again, those two electrons count towards this one, and they also count towards this one. They're being shared between these two. And so that's why we would find fluorine would be a diatomic molecule, because it's not going to, it wants to be stable, and a way to be stable is to just share these electrons here with each other. And so they become bonded in order to gain an octet in each one. And it would be the same thing for chlorine, bromine, and iodine. They would have the same exact structure, because all of these have 7 valence electrons. If we look at, let's look at something besides a diatomic molecule. How about, we'll look at water, H2O. So in this molecule, we've got 2 hydrogens and 1 oxygen. So if I draw out, here's oxygen. Oxygen is right here on the periodic table, so it has 6 valence electrons. So if I draw those in, 1, 2, 3, 4, 5, 6. So 6 valence electrons, and then I've got 2 hydrogens. So I've got 2 hydrogens. Each hydrogen has 1 valence electron. Now remember, for this, hydrogen just wants to have 2 electrons, and then it's stable. Oxygen wants to have 8. And so if I look at this, it makes sense that I would have 2 hydrogens for every 1 oxygen, because this hydrogen here can, these 2 electrons here can be shared with each other to form a bond, and this electron and this electron can be shared with between each atom to form a bond. And so what I end up getting is oxygen. I've got a bond on each side with hydrogen. Oh, thing froze up. And then these here are not bonded with anything, so we just leave them like that. And there's my H2O molecule. So notice, let's count up the electrons on each one. So I've got hydrogen. It only needs 2 electrons to be stable, which is coming from this bond right here, right? So these 2 electrons will count towards this hydrogen as well as the oxygen. So each hydrogen has 2 electrons in its outer shell, so it's stable. If I look at oxygen, it has 1, 2, 3, 4, 5, 6, 7, 8. And so each atom in this has a full outer shell, and it's good to go. Let's try another one. How about CH4? So I've got carbon with its 1, 2, 3, 4 valence electrons, and then I've got 4 hydrogens. 1, 2, 3, 4. Each hydrogen with its 1 valence electrons to work with, carbon with its 4 valence electrons to work with, and hopefully this is pretty obvious to you. Each hydrogen is going to bond with each of these outer shell electrons, and so I'm going to have hydrogen bonding with this one. I'm going to have a hydrogen bonding with this one, hydrogen here, and a hydrogen here, and so that forms a bond. That forms a bond, another bond, another bond. And if we count up the electrons, so each hydrogen has 2, carbon has 2, 4, 6, 8. All of those have an octet, and they are good to go. Let's do one more, just to really drive this point home. How about NH3? I've got nitrogen with its, well, let's take a look real quick. Nitrogen has 5 valence electrons. So 1, 2, 3, 4, 5. And so with this, I've got 3 hydrogens. 1, 2, 3. So it should be pretty obvious again. I'm going to have a hydrogen that's going to want to bond here. Another hydrogen that's going to want to bond here, and a hydrogen that's going to want to bond here. Forms a bond on each one, and if we count up, they should all have a full octet. Hydrogen has 2, this hydrogen has 2, this hydrogen has 2. Those are good. Nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. And that one is done as well. Now, these are all just single bonds that we've been looking at for all these, okay? So a single bond is just 2 electrons that are shared between each one. We can get into, and we're going to get into next week, double bonds and triple bonds, but for right now, we're just going to look at the single bond. And that is how we represent a single covalent bond with a Lewis structure.